didn't notice until I was
Okay, you guys. As you noted from my email over the weekend, we're just going to keep this week's schedule the same. So today will be a review for Chapter 16. Wednesday will be Chapter 16, and Friday will be a review for the final exam. Also, tomorrow evening, I will try to get in here, say around 8 o'clock, for an office hour for those people that have some last-minute questions. Oh, and I should refresh this page because, yeah. So the worksheet that we're going to do in class today is here, and the answers are here. So that's the goal today, is to work on this worksheet with whoever's around you or whatever group you normally work with. And I also sent around an email about a notation summary that I was putting together, which you can see here. This is an attempt to collect all of the notation that you encounter in Chapter 16 in one location with very brief descriptions. If there's something that you've encountered either in Chapter 16 or on the web work that's not here, please do let me know and I'll add it. This is a page that might be useful for when I teach this class in the future. So if there's something missing that you'd like to see added to it, please do let me know. So this will be good for studying if you're a little bit wary about the variety of notation that you encounter in this chapter. This hopefully will clean it up. Yeah.
What time is the final exam?
The final for this class is 9 a.m., 9 to 11. It will be a cumulative final exam, and it will not stress any particular chapter over any other chapter. The length will be roughly the same. I will write the exam to be completed by the average student in about an hour. Okay. Another thing that I'd like to add.
Time might be at the same time 20th century physics is.
No, I'm following the registrar schedule, and so if all of us that are following the registrar schedule, that can't happen. If you want, I can show you the.
Tuesday.
Oh, it's Tuesday? Yeah. We can see the demo in class. I thought I had Thursday.
I mean, it's intentionally developed that way so that there's no conflicts like that. But if you go to my to the class syllabus, down in the final exam section, there's actually a link to the registrar's page that tells you final exam times for all of your classes. So if you're not sure about a particular final exam, you can go there and look at the fall semester final exam schedule, and you'll see this class, its first meeting is, or its meeting class is, its meeting time is 2:30 Monday, Wednesday, Friday, which tells me that it's 9 to 11 Thursday, December 13th. But all of your classes and your final exams can be found, your final exam times can be found here. Okay. I also created a web work review for Chapter 16 that is now, in fact, currently open and will close tomorrow evening at 5, I think. It's not really important when it opens and when it closes, to be honest. Remember, I'm not looking to grade it or anything like that. This is purely for your own study purposes. So I just went through and picked a few problems from each of the major areas of study that we did in Chapter 16 and slapped them in here. Please do remember also that I'm committed to getting some sort of graphical question on the exam, some sort of field or something like that. So there are a lot of those kinds of questions, maybe not in this review, but certainly in the larger collection of web works that we did for this chapter. So pay particular attention to those guys. So what I'd like to do is answer questions that you may have had on the most recent web work or book problems, and then we'll go and do the group work. Ryan, did you have a question?
Web work, true or false?
Oh, yeah.
Whichever one that was.
Yeah, let's talk about that. I don't remember. Was that 3, maybe? 3. Okay. So these questions are all the same. The only thing that was different is they may have been slightly shuffled order for different people, but the questions are all the same. So are the following statements true or false? Let's talk about each in turn. If f is a vector field in 3 dimensions satisfying the divergence of f equals 1, and S is a closed outward-oriented surface, then the surface integral is equal to the volume enclosed by S. This is very similar to an exercise that you did in homework, speaking of which. You can put your homework in the box there. True or false? I hear falses, I hear trues. That's the divergence theorem, right? Let me get my writing surface prepared here. So the divergence theorem, regardless of what f is, as long as this is a nice outward-oriented closed surface, the divergence theorem says that this has to be equal to the area over the integral over the volume of the divergence of f dv. Now let's go back to the question. If the divergence of f is equal to 1, then this is 1, right? And that's the volume of E. So this is true. That's it. That's the extent of it. The next one. If f and g are vector fields satisfying blah, then f is equal to g. True or false? Give me an example. Counterexample, excuse me. Andy?
X squared, y squared, z squared, and x squared plus 5, y squared plus 5.
Just throw in some constants. Yeah, the constants go away when you differentiate. Sure. Okay, so those two will have the same divergence, but then they're not equal. And you can just throw in any constants that you want, and the constants get wiped out by the divergence. So 2 is false. 3. 3 is a bit tricky. It's trying to lead you astray. I heard a false. It's trying to make it look like the divergence theorem, but it's not the divergence theorem, primarily because this surface S is not a closed surface. It's a flat disk. And the divergence theorem only works on closed surfaces, surfaces that enclose some volume. So right there, you know, it's sort of leading you down that path, and there's no path there. It just doesn't make sense. In fact, I can find an F. I can find an F for which the divergence is not 3 over pi. Certainly, if F is equal to this, it's like church, isn't it? You know, passing around the basket. Yeah. So if you want to drop some 20s in there, no problem. Okay. So certainly if you take, for example, oh, I don't know. Yeah, let's take f equal 3 over pi. Okay. What's the normal vector for this surface? It's a flat disk. It's not really clear, but we can just pretend it's a flat disk parallel to the xy plane for the sake of argument, because we're allowed to choose anything that sort of violates the that makes this thing false. So yeah, let's take a flat disk that's parallel to the xy plane. Therefore, the normal vector is 0, 0, 1. So let's throw that in there. Okay, so then if I compute f dot n ds, what I get essentially is the integral over the surface of, let's call it dA, and then there's a 3 over pi in here from the dot product. That's 3 over pi times the area of S, and the area of S, I've already forgotten. Was it 4 pi? Okay, so That guy goes away and you get 12. So there's an f that makes that true. What's the divergence of that f? Zero. In particular, it's not 3 over pi. So this just was a weird, it's trying to lead you down the divergence theorem path, and there's no divergence theorem to be applied here because it's not a closed surface. Okay, moving along then. So that one, number 3, is false. Number 4, if f has a vector field in 3D, then the gradient of the divergence of f is 0. It's false. In fact, pretty much any non-trivial f that you can drop in there will fail that test. So if you're looking for a counterexample, just do like x squared plus y squared plus z, x squared comma y squared comma z squared. It'll fail. Okay, so 4 is false. 5, if f is a vector field, what was 4, what was 4 trying to lead you down? What path was it trying to lead you down? Certainly if you take the gradient of a scalar, sorry, no, not the gradient of a scalar. What's it? A constant. The gradient of a constant is going to be 0. Where's this? Sorry? Where's this thing trying to push you?
Compression or rotation.
Yeah, it's the relationship between the curl and the divergence. Right? Divergence of the curl, curl of the divergence. Okay. But the gradient and the divergence don't share that relationship. It's just the curl and the divergence. 5. If f is a vector field, yada, 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 true or false? True. It's the divergence theorem, right? Okay. Everybody okay with that now? Other questions from this assignment? Andy? Number 5. Yeah, good. Okay. You want to run this thing. First of all, this is a divergence theorem problem, not surprisingly. And you're asked to find the flux of this thing across this peculiar surface. I don't know if you can visualize the surface. There's an inner sphere and an outer sphere. So there's this thick shell between the two. And then there's a cone that comes out and sort of picks off a piece of that thing. You're going to want to do this in spherical coordinates. And I suspect perhaps what you're asking about are what are the limits of integration?
Yeah, that's mostly.
Okay. So you take the divergence of this thing. That's fairly straightforward. That's going to be 3 times the quantity x squared plus y squared plus z squared, right? Okay, good. This guy, rho, if you go spherical, rho goes from what to what? If you're outside of this and inside this? 1 to 3. Good. Now, phi, you're trying to stay inside this cone. And it's a right angle cone. At the angle that it makes at the point is a right angle. So phi goes from what to what? 0 to pi over 4. And then theta all the way around. So the integral is going to be rho goes from 1 to 3. Phi goes from 0 to pi over 4. Theta goes from 0 to 2 pi. The integrand, what does the divergence of f turn into in spherical coordinates? 3 rho squared, and then you get another rho squared sine phi d rho d phi d theta. Okay. Yeah.
Why would it be pi over 4 to pi over 2?
Why wouldn't it be pi over 4 to pi over 2? Let me draw you a picture. So you've got this right angle cone, right? And you've got this one sphere, and then you've got this other sphere. Remember what phi measures. Phi equals 0 is here, and this is phi equals pi over 4 out here. And what we're interested in is the stuff that's between these two spheres. Okay?
How would they measure it backwards? Is there any way
It is actually annoying. So by backwards, I think what Henry means is why isn't phi equals 0 down here? And then this is positive and this is negative. In fact, in my differential geometry class, we actually use that parameterization for spherical coordinates. It's called geographic parameterization as opposed to spherical coordinates. Spherical coordinates, you know, I think that's a really good question. I would be interested to know in the answer as well. Why did they choose that versus making phi equals 0 the equator, and then the North Pole would be pi over 2 and the South Pole would be minus pi over 2? I don't know. There's a lot of nice things about that parameterization, not the least of which the cosine of phi is always positive on that range, and that makes life really easy in differential geometry. Whereas here, the cosine, it's positive, and then it goes to negative, and it's really annoying. Anyway, that's an aside. Does that answer your question, Andy? Okay, other questions? So divergence theorem is a little more manageable than Stokes' theorem, perhaps? Yeah. The big thing with Stokes' theorem, and I encourage you to do the book problems in particular, is deciding with Stokes' theorem whether you want to do a contour integral or whether you want to do a surface integral. That's really the big one. The other thing when you're studying, you know, when you get a big pile of symbols like this, the only way to really get good at parsing these things is just to do a lot of problems. Okay? Do a lot of problems. Make sure by Wednesday that you are simulating test conditions. And by that I mean you're able to do problems with just a piece of paper and a pencil. No book, no Wolfram Alpha, no nothing. Okay? I will give you problems that in the end are going to work out fairly nicely. But I also am not going to be afraid, you, especially people that have been doing a lot of problems, you know that these problems sometimes present themselves as absolute nightmares. They just look terrible. But then something happens in the problem to make everything nice, right? A z is 0, or the curl is really simple, or the divergence just kills everything, right? I definitely am going to hit you with problems like that look really scary up front, but then turn into nice stuff after you hit it with the right theorem, or after you parameterize it and there's a z equals 0 or something like that. So don't be, if you do enough of these problems, you'll avoid that sort of gut fear factor of looking at that and saying, oh my God, what am I going to do with this? If you do enough problems, you'll get over that. Okay, any other questions before I turn you loose on group work? Let me make sure I've answered or talked about everything that I wanted to talk about. I don't even remember where it is now. Oh well. All right, so let me give you this work. You don't have to work in any particular order, but note on the back is a graphical type problem. It's a fairly simple one, and I'm not as totally happy with it as I had hoped I would be. But I did figure out how to make it in Maple this morning. So you can expect something on the exam that'll be graphical and interesting.
Yeah, I will so do that. Just say.
And then also, this is
Guys, I don't know how far you've gotten, but let me just sort of broad strokes this thing and get you guys on your way. So as I mentioned, I posted the solutions to this worksheet online. The first problem was that curve x to the fourth minus 6xy cubed equals 4y squared. That was a bit of a red herring. The idea here is to recognize that that this is a conservative force field, and therefore the fundamental theorem of line integrals, it comes into play, and in fact this is path independent. So you can completely ignore that thing about the curve. This is really an issue of finding f, whose gradient is this, and then plugging in 2, 1, and 0, 0 and subtracting. Okay? So again, I warn you that these problems tend to dump a lot of stuff on you, but if you're thinking about it right and you've done a lot of problems, you're going to recognize, you're going to be able to see through all the clutter and just get right to a fairly straightforward integral. The second one was a Green's theorem problem. So let me contrast that with the first one. This is not a Green's theorem problem because Green's theorem only applies to closed curves that enclose some area in the plane. So problem one was really, there's no way to use Green's theorem there. Problem two, on the other hand, is a closed curve, and in fact, this little bubble here on the contour integral symbol, that's a mathematician's way of signaling to you that this is a closed curve. It's not required that you write it. It's just something that mathematicians like to do when they're working with a closed curve. So it doesn't mean anything different from a regular contour integral. Here you would apply Green's theorem and qx minus py over the integral in the interior. And I mentioned that I think if you reverse the order of integration in the last line there, that you can avoid an integration by parts. Number three, verify the divergence theorem. So in this problem, the idea was to do both the surface integral and the volume integral and show that they're equal. The surface integral is a bit tricky. You have to actually do three integrals, one for the top, one for the side, and one for the bottom. The top and the bottom integrals, and this is something that you should also take note of, when you're doing a surface integral and you're dealing with a planar region, often those surface integrals are pretty straightforward because the normal vector is constant. So it doesn't introduce much complication in your life. And the other nice thing about, for example, these two guys, the top, you can set z equal to 3, so this is just a 9 right here. And the bottom, even better, z is equal to 0, and so that's a 0 right there. And the normal vector on the top is just k, and the normal vector on the bottom is minus k. So when you dot those guys, all you're really doing is picking up this third coordinate. So that makes life a little bit easier if you're astute. On the side, let me see where the side one is. On the side, you have to parameterize the cylinder like this. This is the cylinder of radius 2. U goes from 0 to 2 pi, V goes from 0 to 3. And this one, you just have to grind it out. So you find RU cross RV, that's this guy here, and do the dot product and the substitution and grind it out. Okay, let's keep going here. The two integrals, if you do the two integrals, you'll get 84 pi for both of them. The right-hand side is the volume integral, and that's a little bit more straightforward. You compute the divergence of f, which works out to this. And when you're doing an integral over a cylinder, if you have the option of switching to cylindrical coordinates, I recommend that you do so, and that's what I did here. And when I switch to cylindrical coordinates, I get r dz dr d theta here, so I get an extra factor of r. Problem 4 was a bit tricky. It's not something that I would throw on an exam. It was really just to get you to think a little bit about the divergence theorem and some of its implications. The idea here is I have this, this surface integral that I'm interested in computing. Oops, let me get rid of that. So I'm interested in computing this surface integral. And it's a real bear. So if I look at this surface and then I go back and I look at the function that I'm trying to deal with, if you just sort of crank this thing out and you try to do that surface integral with this function, it's a real mess. So a clever application of the divergence theorem says, okay, this is not a closed surface, but I can make it closed if I tack on this thing on the bottom. So I make it closed, I apply the divergence theorem, and then I subtract this thing on the bottom, which is presumably a much easier surface integral. And it is, because not only is z equals 0, but it's a plane, so k is, the normal vector is just pointing down in the minus k direction. If you do that, the divergence of this f is not surprisingly pretty straightforward. It's z squared, it's z squared here, and y squared, and x squared, which is just rho squared when it's all said and done. So the volume, the divergence part of this thing is this integral. and then I subtract off the surface integral that I get by tacking on that extra thing on the bottom, which is pi over 4. And in the end, it works out. Okay, number 5 was really just a repeat of the homework that you turned into me today. Slightly different wording, but essentially the same. Show that the volume of E can be written like that. So you write that equation, you apply the divergence theorem to this thing, which is that. You drop in the fact that, here's F. You drop in the fact that the divergence of F is 3, and it just falls out. So that's literally the homework that you turned in today. 6 is Stokes' theorem. Use Stokes' theorem to evaluate this thing. Whenever I say use Stokes' theorem to evaluate a contour integral, that's a little bit easier than deciding which one to use, because now you have to do a double integral. I'm using some notation here that you may or may not remember from section 2, but F here is z squared comma 2x comma negative y cubed. And that's just an f dot dr integral in a slightly different notation. So you have f dot dr, and you want to evaluate it around the circle, oriented counterclockwise. Essentially, you convert this thing to a surface integral, where you take the surface that just is the plane passing through that circle. Why the plane? Because you get a nice normal vector here, and out falls a fairly straightforward surface integral. Problem 7 is a center of mass problem. This is really just, do you know how to do a surface integral and throw in an extra density function? Okay, and I've summarized all of the center of mass stuff there for you: x bar, y bar, and z bar. And again, you were just asked to set this up and discuss, but not evaluate. Okay. I haven't put the answer to the last one up there yet, but let's talk a little bit about it. Let me pull that up. Like I said, the last one, I'm okay with some of it, but other parts of it I'm not entirely pleased with. So here's the last one. You've got these 3 vector fields depicted here, and notice I state explicitly that the curve is oriented counterclockwise. That's important. Remember that when you're computing these f dot dr integrals, if the angle between f and the path is acute, then you're getting positive work. If it's obtuse, you're getting negative work. That's the key principle here for part A. So as you look at the first field, you see that as I go in this direction, counterclockwise, I'm typically working against the field. And I have obtuse angles everywhere. And so positive, negative, or 0? Negative. What about the next one? Also negative. And the last one? 0, why? It appears to be perpendicular everywhere. When you're answering a question like this for me on the exam, please do put a brief explanation after, because it may be that maybe you look at this thing not quite the right way, or you just misread the vector field. But if you wrote on there, let's pretend that there were some places where it wasn't quite perpendicular, and you wrote 0 because the path is perpendicular, I'm going to give you a lot of credit there, because basically you knew what you were talking about, but you just kind of misread the field somehow. So if you can give a brief explanation after that you give me the opportunity to give you a little bit of partial credit. The second part of this problem is to say whether f is conservative or not conservative. This is not so bad for the first 2, but for the last one it's a little dicier. And so I probably wouldn't ask this question of you for a field like that on the exam. That said, there are fields where I might ask you this question. The first 2, though, not so bad. Remember that if f is a conservative field, then the integrals are independent of path. The line integrals are independent of path. So if you can find 2 lines, 2 paths from, say, 0, 1 to 1, 0 that clearly give different values, then F is not conservative. Let me give you an example. Maybe I can write on this. I don't know. No, I don't think I can write on this. Let's talk about a path that starts at 0, 1 and goes down to 0, 0 and then over to 1, 0. I don't know if that's 0, but I know it's going to be relatively small because these force vectors get small. They're clearly small along the y-axis, and they grow along the x-axis, but they're clearly small. So that's going to be a relatively small integral. On the other hand, if I go, let me see. I'm trying to think of a better path that would be more convincingly large. If I went sort of along here, I don't know actually. I have to think about this now.
I thought that one was conservative.
Yeah.
Because
I think it might be
even though
conservative.
they're small, you'd be going in the direction exactly, whereas if you were like curved, you wouldn't quite be moving in that
Yeah, and this again leads me to the point that I was trying to make earlier. It's not entirely clear here that this is conservative or not conservative, because you can sort of draw curves on this thing all day and maybe not convince me, or maybe not convince yourself that it's conservative. So I would back off from that. Let's move to the second one though and use that same idea where it's much clearer. So I will give you fields where these things are much clearer. And again, this is my first attempt, so bear with me. Let me use that same idea here to show you that this guy is definitely not a conservative field. If I start here at 0, 1 and I go down to 0, I get nothing, right? Because I'm moving perpendicular. And then if I move from here to here, I get nothing because, again, I'm moving perpendicular. And then if I go back around to where I started, I get a negative number. If it were conservative, a closed path has to be 0, right? And it's not 0. So I've clearly shown that that guy is not conservative. The other two may, in fact, be conservative. I don't remember what vector functions I used. And frankly, the only way to really prove it is to do the test for conservativeness that I actually on the functions that I actually use. So I'll do a better job on the exam, I promise. But that's the idea, is to use your knowledge of conservative fields to try to show whether it's conservative or not conservative. I will let you know via email sometime in the next 24 hours whether I'll have an office hour tomorrow night at 8 o'clock, 8 p.m. And don't forget my regular office hours at 2 p.m. and 10 a.m. tomorrow as well. Have a good, oh, and don't forget the web work. And see you Wednesday. The homework box, everybody get their stuff in the homework box? If not, bring it up.